Yeah. So today I will talk about ultrafast dynamics of antiferromagnets, focusing on the switching between the different states. And in order to switch, we need somehow to introduce dynamics of the magnetic sublattices. And this could be done in two ways. So one way is to pump spin current into antiferromagnet, and this absorbed spin will induce rotation of magnetic sublattices. And this kind of torque is called anti-damping torque. Another way to induce magnetic dynamics is to use the magnetic field which is created by spin current via SD exchange, for example. And this kind of torque can induce spin flop transition, so the switching between different states. And this type of the torque are called field-like torques. The point is that this type of field-like torques induce switching to the final state, which is well defined. However, we have a problem if we use the DC spin currents, then this spin field-like torque is very small because of the properties of antiferromagnets and compensation of the net magnetic moment. However, nowadays we can use a very short current pulse, which can be created optically or by the current. And in this case, instead of DC spin currents, we can have time-dependent pulses. And the aim of this presentation is to discuss new phenomena which can appear due to the time dependence of these spin currents. So in my talk, I will try to convince you that these time-dependent spin orbit torques can induce fast switching or ultra-fast switching, at least compared to the time scales of ferromagnetic materials. Moreover, I will try to convince you that using these time-dependent ultra-fast pulses and by tailoring them in a proper way, we can induce reliable switching between different states. And of course, in the real samples, we should also take into account the effects coming from the lattice and magnetoelasticity. And this I will also discuss in my talk. So this is an outlook of the talk, and I will consider three problems: ultra-fast time-dependent switching in non-collinear antiferromagnets, collinear antiferromagnets, and we'll discuss shortly magnetoelastic effects in nickel oxide related with the oscillations of the T domain walls. But first, I would like to remind you the kinetics of antiferromagnets in presence of the anti-damping DC spin orbit torque. So this spin orbit torque can act on an antiferromagnet in two ways. If the current is relatively weak, it induces rotation of the magnetic sublattices from its equilibrium state. However, if the current density is higher than some critical value, then this current can induce magnetic dynamics. In fact, it induces oscillations of the magnetic moments in the plane which is perpendicular to the orientation of spin. The problem, of course, this rotation is very fast, which is nice because it scales with the frequency of antiferromagnetic resonance and can reach terahertz range. Also, this precession frequency can be tuned by the current density. However, this physical phenomena is not appropriate for the switching because the rotation stops only when you switch off the current, and you do not know what would be the final state of the system. So now we decided to study how we can attack this problem using time-dependent current pulses. And for this, we decided to start from a more complicated system, an antiferromagnet, which has 3 magnetic sublattices. Surprisingly, this type of rather complicated material can be quite well grown on the heavy metal in different geometries. And this allows to tune orientation of the spin polarization in such a way that the dynamics of the system can be optimized. So what we did, we considered dynamics of this system in the geometry when the spin current polarization is exactly perpendicular to the easy plane of for the magnetic moments, and studied these dynamics in presence of 2 types of the spin torques, spin anti-damping torque and field-like torque. So what are the results of this study? First of all, this type of material like manganese 3 tin or similar, they have 2 states which could be physically distinguished, and these states have opposite orientation of the sublattice magnetization, and also due to the weak DMI interactions, they can show small non-zero magnetization which can be measured, and in this way the states could be distinguished. Then when we apply a spin current, which is DC, this system shows rotation in easy plane, which is very similar to the behavior of the collinear antiferromagnet. This rotation takes place with a frequency which can be even larger than the frequency of the antiferromagnetic resonance, and on top of these oscillations we have a kind of the nutations. However, this type of behavior again is not applicable to the switching between different states. However, we can try somehow to fix the final state by applying the external magnetic field, for example. So we tried to look at the phase diagram of the system in presence of current and the magnetic field, and we were disappointed in the way that the system has equilibrium states in some range on field and current, and of course the magnetic field splits equilibrium states, but still the rotational states are not very affected and they cannot induce reliable switching. However, the positive outcome of this study was that exactly this phase diagram was observed in the experimentally quite recently by Otani group. Then we decided to look at the time-dependent pulses, and for this we studied dynamics of the system by applying pulses of different time durations. So we used Gaussian pulses, and we played with the amplitude of the pulse and with the pulse width. So what we found, first, the dynamics of the system is shown here. So this is a phase diagram of the material in absence of any field and current. And then the short current pulses, what they do, they kick up the system from equilibrium state to some point in the phase diagram. And then we can get a switching if this kick would be properly trailered, because then we can kick the system to this blue area, which end up in the state with opposite magnetization. However, we should be extremely careful, because if we apply too strong initial pulse, then the system will rotate too much and end up in the initial state. So how can we tailor these pulses? First, we studied the effect of the anti-damping torque, and we found out that if we use only anti-damping torque, we should be very careful, because depending on the pulse width, we can have full switching to the final state, or the system can return back into the initial state. However, when we took into account the second effect coming from the time-dependent spin current, we find out that this part of this torque can stabilize switching to the final state. So what you see here we modeled the dynamics of the system for the same time pulses with the same time duration, and for all possible pulse widths we get reliable switching. And the reason is very simple. Here you can see the separate contribution of the anti-damping torque and field-like torque. And the sum of this torque gives a very special shape of the pulse, where at the initial stage the system is accelerated quite fast, but then decelerated and pushes a system into the proper final state. So to conclude this first part of my talk, I would like to show the real experimental diagram which shows switching in manganese 3 tin. These are electrical measurements, and of course they show the switching at the very large time scales compared to this ultra-fast switching, but at least the theory shows us a route where we can achieve a certain progress in switching. Then we decided to look at the switching in a more traditional material, nickel oxide, which is well fitted for spintronic applications. And this material is well known, and it has only 2 magnetic sublattices, so it's a collinear antiferromagnet. However, if we look at so-called spin domains, there are 3 different possibilities. So the spins in the 111 plane, the easy magnetic plane, can be ordered in a point in 3 different directions, which make 120 degrees. Yeah. So then this system can, in principle, be used for switching between these different S states. And the question is, how can we induce this switching, and how can we control this switching? So again, we studied dynamics of this antiferromagnet, but in this case, we look only on the anti-damping, the effect of the anti-damping torque. And then the phase diagram of this material is very similar to the non-collinear antiferromagnet, but now we have 3 different states. So if we apply a very short pulses, we should tune it in such a way that we end up in this final state, red or green or violet. So we studied the dependence of the final state on the pulse duration and the density of current, which can be applied to the system. For modeling, we used the rectangular pulses of different duration. And here you can see that in principle, we can switch to any state of the system by tuning the current density and pulse duration. But of course, we should be very careful because then the small mistake can throw the system into other state. However, this way of tuning the system seems to be very inspiring. I would like to show some recent results of the Cui and others, they used these ultra-short pulses for stimulating emission of radiation, but then we can see that these pulses can be tuned very well, and then we hope that we can we can reach this switching to different states. And the way how we can also induce this switching is to follow these ultra-fast magnetization experiments in ferromagnets. For this, we can use a combination of metal and optical pulses. And then the pulse which will induce successful switching should have exactly the same shape as we observed when we combined anti-damping and field-like torques. So the second part of my talk can be concluded as in principle we can switch very fast in collinear antiferromagnets using for example, optical pulses or current pulses, but then we have a lot of problems with tuning the signal in order to get the proper final state. However, this is not the only problem which we have working with, for example, nickel oxide, because as we have shown in recently in Mainz, trying to switch between different nickel oxide states by DC current, we found out that the samples which we used, they do not have S domains. They consist of T domains, and these T domains show very strong magnetoelastic effect. So in order to work with the real samples, with real materials, you should not only play with the spin current, you should also take into account how the lattice reacts on these spin currents. So now I come to the third part of my talk, which will be more widely discussed by David Bossini from the experimental side. He will present tomorrow at 10:40 the results of the magnetic dynamics in nickel oxide with account of magnetoelasticity, but I will give a short overview of the theory. So the nickel oxide has different types of T domains, and these T domains, they differ in orientation of easy planes. So they are twin domains. Yeah? And then if we try to induce switching between different states, maybe we would like to induce domain wall motion in this system. So what could be effect of magnetoelasticity in this case? First, let's consider magnetic switching with the use of the domain walls without magnetoelasticity. In this case, we have two regions with different orientation of the Néel vector, and then the dynamics of this domain wall induced by any external field or current is the translational motion from the left to the right. This can induce switching, and this switching can be very fast because the domain wall velocity is fast. But this is not the case in nickel oxide. Why? In nickel oxide, we have T domains, and these T domains have not only different orientations of the easy planes, they also show very strong distortion in left and right domain. And this distortion distorts the profile of the magnetic anisotropy. So in this case, we in a multi-domain sample, we have regions with a different profile of the effective anisotropy. What would be the result of such modification? If we try to move the domain wall in this case, the magnetic part of the system would react very fast and will move quite easily. However, deformation is very heavy and is very slow, and it will stay as it was before the external stimulus. So when we shift the magnetic domain wall with respect to the elastic system, the part of the sample will be in the state when the magnetic moments point into the heavy direction. And this costs energy. In other words, the domain wall in this case will be pinned by the magnetoelastic interactions and will oscillate around its initial state. So what we can learn from this kind of the dynamics? We calculated the magnon spectra for the multi-domain sample of nickel oxide. And we found out that the spectrum looks like very similar to the bulk single domain sample. However, the structure of the modes is very different, and each magnon mode of this low frequency branch, it is hybridized, and it consists of the propagating and localized modes. What does it mean? The magnetic system is a nonlinear system, and if we excite one of the magnon modes by applying the optical pulses, then we can also excite oscillations of the domain wall. And these oscillations of the domain wall through the paramagnetic resonance, for example, can excite other modes. So this magnetoelasticity can be a tool for manipulation of the magnetic dynamics, which can help us to tune the switching processes. And this what exactly was observed in the experiments of David and others. So the excitation of the terahertz mode in nickel oxide excited also domain motion, and as a result, we observed the other magnon modes in this system. So if we would like to switch nickel oxide, in any case, we should take into account these complicated dynamics which is induced by magnetoelasticity. And also, if we try to, we can try to overcome this strong magnetoelasticity. And here I would like to show you very recent results. This is archive which was published 2 days ago. From also Mainz and Kaiserslautern group. So this is a kind of ultra-fast demagnetization. So application of a quite strong optical pulses which heated the sample induced the reduction of the magnetic moments of nickel oxide, but as a consequence, we can anticipate that also magnetostrictive effects were diminished, and this process can facilitate switching to the other state. With this, I end up my talk. So I discussed switching with a short pulses in a non-collinear and collinear system, and discuss shortly dynamics in presence of magnetoelasticity. And at the last slide, I would like to show my collaborators. Vadim Loktev, with whom I worked for a long time in Ukraine, a very nice collaboration with Michel Viret from France, and of course David Bossini and Stefano Bonetti, my best courses. I shouldn't say this. So thank you for your attention.